Hello everybody, today we'll be doing a hard problem called minimum window substring. Given two strings s and t of the length of m and n, respectively, return the minimum window substring of s such that every character in t, including duplicates, is included in the window. If there is no such substring, return the empty string. So the test case will be generated such that the answer is unique. A substring is contiguous sequence of characters within the string. So here we go. We have this string, we have t, and our output is b, a, and c. Okay, the minimum window substring is b, a, and c, and that includes a, b, and c from the string t. Here, the minimum window to find t in S is A, because the entirety of the string S is the minimum window. Here we have an example of an A and a double A, and as you can see, it was not possible to fit the two A's from T into the window of A. Yeah, so it's not possible. So return an empty string. Does that cover all the edge cases? How about an empty string? Would that be an empty string for the output? So the length has to be 1. There is no empty string that's possible. This is basically the minimum, and this is another edge case. So two edge cases were basically given to us. We did not need to look for any edge cases at all. With that, I think we have all the possibilities here, and let's think about the time and space complexity that we're trying to aim for. The time, I think it's O of n, because, O of m minus n, because we are looking for this substring in this particular item here. So n minus m, sorry. So because m being the length of S1, S, and n length of t. So we're going to n minus m, and space is going to be spent on basically, it's like the same as the previous problem, I think, where we have to use a space of the sliding window, which is the size n. And that should be all. Yeah. Sorry, it's m minus n, because, yeah, length of s. Okay, give me a moment to think about the next step, which is going to be the matching. What match do we have? The match is going to definitely be sliding window. Is there anything else that we need to think about? We need a hash map, probably, and just come up with a plan quickly. The plan is to find the item in the minimum subs window. So basically, we create a window, with A, B, and C. 2. Reduce the window and get min. Min size, I guess, the minimum min window size. Reduce the window until with string t, and until window is without t, and that's it. I think that's all we need to do, and at the end, return that minimum window. Right? That's all we're trying to do. Okay, so what if we can't find the item inside our window? If there's no window with that item, well, probably zeros like handle t is greater than s, return empty. So how do we know that we're not able to create a window? And we could use a flag. What is that flag? Question. What if window not found? So maybe flag. Maybe flag it. If the window is not found, what would our minimum window size be, right? Our minimum window size would be -1. Yeah, we'll set it at -1. And if it doesn't change, wait, sorry. It's length of s. Length of s. So +1. So if the minimum window size is the length of s, right? +1, then it's impossible for us to get. It's impossible to get that in index, right? So yeah, that's impossible for us, right? And because it's impossible, we just go like, yeah, it was not found. If it's anything, yeah, if it's anything else, then it has been found, and yeah, that means we can deal with that. We can work with that. Yes. Okay, so that's our plan, and let's get started with our implementation. It shouldn't be too hard. So let's get m and n. So m is going to be the length of s, and the length of t is going to be n. So this is like my 5th problem today or more. I don't know. I'm feeling like a little bit exhausted, but I think we should do at least 5 problems to build up endurance during the interview. Because the interview is like maybe 4 or 5 problems long, and yeah, we're gonna get tired. And so if you do them consecutively at like 5 problems, like a couple hours of this in a row, I think it would be helpful. Okay. So what's next? M and follow this. So if m is greater than n, sorry, if n is greater than m, return empty string. Otherwise, let's create a window with size string t. So let's create the hash t and hash s. Hash s is equal to the counter of s. Hash t is equal to a counter of t. So that's the entire window, right? So what happens here is, like, while the window size exists, actually we need to grow the window size until we find the minimum window. So we have the hash of t, right? That means that's exactly all the characters that we need. So we have the hash of t, but we need to grow our create a window. We need to create that window. So how do we create that window? So I is equal to 0, and j is equal to 0 as well. And we're gonna grow this window. So grow window. Yeah, we're gonna create this window. So while hash s equals counter, hash s. Okay, that's a problem because we need to make sure hash t in hash s. I don't know if that will work. I really don't, but that's the idea. The idea is this. So if the count for t, like A1, B1, C1, is inside a item here, this window, and we have A1, B1, C1, we're going to keep going. I don't know if this will work, right? I really don't know. So I'm gonna test it, see what happens, and then we'll go from there. There's lots of things I mean, yeah, I don't know. So hash s at string of I plus equals 1, right? And s of I mean I, and then j j plus equals 1. And we're going to do this while I is less than m minus n. Okay. Maybe I should have taken a little walk. And maybe there should be a break. But I am significantly more tired probably. So with that, we should be able to find a spot in which this breaks. And so let's do a break here and see what happens. So break. I plus equals 1. So if this breaks, I don't know what happened. Let's print statement here. Hash t in hash s. I don't know if this will work. Who knows? So let's just like return something like nothing because, well, I mean, let's just run the code. Okay, so it is not possible. We are not able to check if hash t is in hash s. That's not possible. So we need to do something a little bit more like more thorough. So yeah, okay, here we go. Okay, so this is good to know because we know that this does not work. And so we need to deal with this somehow. And the way to deal with it is to make sure that hash at every single character in hash t is equal. So that's what we're testing. Okay. And we're going to create a function to do that. Let me just go write that function out and I'll be back. Okay, so I solved that little problem by creating this is_in window. So we're checking for each character in the hash and seeing if that character is, if that's found in the window, if it's less than or equal to, less than our value, then we'll return false. If it's anything equal to or greater, then we'll return true. So let's run is_in window between h hash s with hash t. So hash s and hash t. That's how we do it. And if it's not, while it's not in window, we're going to increase our window size. Okay, let's try this again. So we need to send this function up, or otherwise set this as a self. So we do need to run that self dot, and let's do something else. Let's print hash t and hash s. Let's see if we can get this. I'm not sure if we'll get it done, but we'll have to keep seeing, learning, and learning more. So did we print? I don't know if we printed anything. So let's print. Oh, that's a break. So that's my bad. Let's put the break afterwards, and let's print. Run the code again. And so we did it. Let's check it out. So we have a counter A, B, and C, and we found A, B, and C. And we were able to use this function to increase our window size until we found something. That's wonderful. So we have gone very far in this problem, and we are getting close to finishing the problem. So let's check it out. So, and then we'll do I plus 1, and basically means that our window size, we'll get our window size, min window size is equal to min of min window size, of course. And this current, how many values there are between j and I. So j minus I. That's our minimum window size, plus 1, usually. That's what we need. So let's check out that minimum window size. Let's set our minimum window size to be our max equals length of s, which is m plus 1. So let's print our minimum window size, and let's see what happens. So return, we also want to retain minimum window size. We also want to retain that item, like the I and the J. So that means we want to get the minimum window size, and we want to get the I and the J. So we set that at 0. So we want to do an if to save our the area between which we need to get our minimum window, or we can just store that substring right now. So store the substring. So result equals a empty string, and we can return the result. So we need to do an if statement instead. So if j minus I plus 1 is less than the minimum window size, then we update the minimum window size. And what we also need to do is that we need to set our result to be result is equal to s of I through j plus 1. So that way we can add this together. So I'm not sure if exactly it will work, but we'll have to find out, and let's run the code. Okay, so we're returning nothing at this point, but I think we're pretty close. So let's see what's going on. Let's print the minimum window size. Okay, so minimum window size is 7. It's -2 for some reason. So I'm not sure how that occurred. I see why it's not occurring. Because we are not reducing, we're not increasing our I. So we need to do that. So once we add the I, we need to reduce the item. So hash s at I at s of I minus equals 1. So with that, I think we are good to go. And there we are. We have an accepted answer. That's exciting. I don't sound very excited. And now let's check the other test cases. And we are wrong. Let's see what's going on. So in the first case, we're okay. In the second case, we are wrong. And in our third case, we are wrong as well. So what's going on? Give me a pause. Okay, hello there again. So I was a little bit tired and I shut myself in to do some debugging, and we have an answer now. So what happened while I was debugging was that I thought, okay, so it has to be then, what we're doing here is checking if it's not in the window, let's increase the window. And while we are in the window, let's decrease the window. And let's get J all the way to the end so we see all the items. And that's pretty easy when doing sliding window. And with that, we keep on iterating through our items until J hits the end. And when it hits the end, we are done. And with that, we are able to complete this problem pretty okay, not too bad. And we just had to do a little debugging here and there to get it perfect. And so yeah, this was a pretty good solution, I think. It's pretty nice and short. There is this case where this where they're equal. We can just straight up make the two counters and set them to be, and then return s. If they are not equal, then we can start growing this window. The reason why we need to do this is because, well, if we try to do this without this line, let's see what happens. Let's see what sort of thing is in my console right now. That's it. Let's just have a single item then, and let's run this code. Oh look, it's correct. Let's just run it then, because we're going all the way to end of M, and we're good to go. It looks pretty good, so we can skip that. And looks like a pretty slow solution. There might be better solutions out there, but let's evaluate this runtime, and let's check it out. So the runtime evaluation is going to be O of like M. So we're gonna have to, while we're not in the window, every time we check if it's in the window or not in the window, and we check it M times. So we check M items. So minimum is M items, and we check it. We check if the items are in the window or not. And every time we check it, if it's in the window or not, we have to check every single item in the window. So that's that's it. M squared operation. Yeah. Check if the item's in the window or not in the window. If it's not in the window, right, then we have to return. If it's in the window, then we don't. So time is m times m, but I think the lookup is actually pretty fast to compare the two. I think we can work on optimizing the usage here of the is in window and to optimize our problem. I'm not sure what we'll do to optimize this, but give me some time and I'll think about it. So after a bit of thinking and realizing that the video was already 26 minutes, we're gonna do a separate video, part 2, where we're gonna change how we look at the window, because the costs that we're incurring right here is because of is in window. We're checking every hash item, and the idea here is that we don't need to check every single hash item. We just need to check the items that's missing or not missing. And so that means that we can bring down the cost to O of 1. And that means that we can bring down our time to O of m, the times that we need to go through the entirety of our window, because we are only checking for the missing items in our window, which is an O of 1 operation every single time. We're going to make at most 2 passes, and we will be going through why 2 passes is because we'll have to slide our window. Our window will move j. Let's say we have many items, right? We will have a j that moves forward and an I that moves behind it. And while j is moving forward, right, let's say j moves forward, we also have to close in with our I. So it's a 2 pass. So it's going to go all the way through. So yes. What we're going to do, we're going to come back in the second video, part 2, where we will be reducing our hash map and only seeking the missing items. And that way, we can bring down our cost to O of m. Yeah, that's about it. I guess it's O of m plus t, because we bring down, we do have to go through m, and, well, we don't do t. We do not do t, sorry about that. So we just straight up do O of m. So that way it will bring us a faster solution. And yes, that's it. So I'll see you in the next one. And yeah.